My name is Dave Luo, and I'm really happy to have this opportunity to talk a bit about geospatial machine learning with everyone. I particularly appreciate how beginner friendly we're trying to make everything. Speaking for myself, I don't have decades of experience. Well, no one has decades of experience with deep learning, but even when it's geospatial data, I feel like I'm always learning something new, and so it's always great to be as welcoming and open as possible with our knowledge. I'm going to share my screen, and I guess you can comment once that shows up. So can you see those slides?
It looks good, Dave.
Okay, cool. All right, let me get this going then. All right, so these slides are also available at this bit.ly link, just to make it easy for you. And so if you want to, you can refer to these later, or you can follow along right now if you want. But the idea is, don't feel like you have to take extensive notes or any notes at all. You can just sit back and listen. So again, I'm here to talk about geospatial machine learning. I'm a consultant that's mostly focused on geospatial data science and machine learning. And I'm presenting some prior work that I did as a consultant for GFDRR Labs. GFDRR is the Global Facility for Disaster Reduction and Recovery, which is managed by the World Bank. And it's a lot of focus on disaster risk management, especially in resource-limited areas. And particularly within GFDRR Labs, we are examining the use of new technologies like machine learning and geospatial data to advance those efforts to reduce our risk and improve our resilience to all kinds of disasters. So in this very intro, beginner-friendly session, I wanted to achieve these 3 goals. We're going to take a quick but hopefully enlightening walk through some common tasks and examples of using machine learning on geospatial data of some variety. I'd love to be able to have you walk away being able to define what supervised machine learning is, what training data for that is, and have a rough assessment of what good versus bad quality training data is. And then we'll also talk about and look at a cloud-native geospatial machine learning data set, given that it is Cloud-Native Geospatial Outreach Day. So just to orient you to this vast world of AI in the popular imagination, here's a bit of a conceptual map of where we're going to go. We're not talking about artificial intelligence and the robots are going to take over, or they're going to become more intelligent than us. That's way above what we need to talk about right now, and there's too much to it. We're going to actually focus much more on the discipline and techniques within machine learning, or algorithms that we use to teach machines to learn, and then within that are techniques around deep learning that are particularly suited for computer vision tasks. So we're talking in this very narrow sense about supervised machine learning. Supervised just means that it's machine learning using labeled data, as opposed to unsupervised machine learning, which is data that may not have labels to them. And we'll kind of talk about extensively what labels are. And we're talking about supervised machine learning applied to computer vision. So teaching machines to recognize things from imagery. And that imagery, in our case, is going to be centered around geospatial data. So in the world of supervised computer vision, we have these 4 major categories of tasks. And there are more, and there are things that intersect within them. But this is a good framework to start thinking about different tasks. So on the left, you have classification, which is just you're given a photo and a label of what is within that photo without any more information about where in the photo it is or how many objects there are. It just, this is a photo of a cat or a dog or a llama or something. Semantic segmentation, though, on the other hand, in the next example to the right, we'll take that same photo and ask or provide labels for every single pixel related to that picture. So in this case, the cat is fully delineated by pixels that represent cats. In this visualization, they're yellow, grass is green, trees are purple, and sky is blue. But notice that the actual underlying image is the same for both tasks. What defines a task is not necessarily the image, it's the label for the image. So keep that in mind. We're definitely going to talk about that later. On the right-hand side, you have, again, the same image, but two different tasks. So for object detection, you're asking a machine learning model to draw rectangular bounding boxes. These are the red, green, and blue boxes around every single instance of an object. And so in this case, there are 2 dogs and a cat. And so it's not good enough to just say, here's one big box around both dogs, but you need to be able to draw a rectangle around every single dog and every single cat. Instance segmentation takes this even further in saying that you don't just draw a box around it, but you have to delineate down to the pixel the boundary around every single instance of every object that you care about. So the 2 dogs and the cat are fully delineated. All right, so we're going to now take those same 4 tasks and look at some examples of deep learning or geospatial data applied to geospatial data. So for classification, we're here looking at satellite imagery. RGB stands for red, green, blue. And so in this case, this is satellite imagery in the visual spectrum that's just capturing, very high resolution images from space pointed at the ground, which is, if you think about it, incredible that we can do that. And for each of these images, we are labeling them as either having a school present in the image or not. And so some of these have schools, some of them don't. And that is the extent of the task. It's just to say this particular square has a school or does not have a school. The next task, which is also a classification task, and this is something that the Radiator Foundation put on as a contest a little while ago, is to classify the category of crop within these various farm fields from multispectral time series satellite data. And so what that means is it's, again, red, green, blue imagery, but on top of that, there's more data beyond the visual spectrum. And so infrared, near infrared, et cetera. So not just things that we can see with our naked eye, but things that the satellite sensor can collect. And it's not just one image, but it's images over an entire growing season of the same area of land. And so within each of these shapes, each farm field is classified as a different type of crop that they grow, from maize to cassava and beans in some way, and sometimes the intercropping or the mixing of 2 crops growing at the same time, which makes this task particularly difficult. Moving on to object detection. Again, remember, we're trying to draw squares or rectangles around each object of interest. In this case, we're looking again at RGB satellite imagery, and we're looking at airports and trying to draw boxes around every single airplane that we see. And on top of drawing the bounding boxes, we're also combining this with a classification task. And so remember, before I said these are discrete tasks, but you can mix and match and combine them together to create more sophisticated tasks. So in this case, we're both doing object detection and classification. What we're classifying here is not just airplane and not airplane, but we're actually looking at how many engines this plane has and what type of propulsion, what kind of engine it is. And so in this case, there are 4 planes that have 4 engines proposed by jet engine and 2 engine jets for the other objects that are detected. Now, moving a bit away from overhead imagery, just to make the point that when we talk about geospatial data, we're not always talking about looking from top to bottom at people's heads, to top of people's heads. We also can use things like street view cameras. And so these are what you might see on Google Maps, where you have a camera mounted on top of a car and it takes a 360-degree image as it drives around of an area on the street. And in this case, this project is taking those imageries and detecting every opening, whether it's a window or a garage opening in these buildings. And the reason to do this is that this World Bank project was looking for soft story buildings, or buildings that have big openings, maybe on the first floor, that are particularly vulnerable to collapsing in the event of an earthquake. And so by having cars drive around, taking these images, and then creating an object detection model that can quickly draw boxes around all the soft openings or garages and windows on the first floor buildings. We can map out in a much more automated way where these vulnerable buildings are. Okay, so moving on to segmentation. We looked at this in the last session, but if you weren't there for that one, just to quickly summarize, this is the labeling contest that Radiant Earth and Azavia is putting on for this program. We're trying to segment every single pixel as either a cloud or not a cloud. And so here, clouds are represented by all the pink pixels, and all the things that are not clouds are represented by green pixels, or sometimes it'll be referred to as background. Taking that to another level, or a more sophisticated level, you may say, is that we can also segment land cover. And so we're just increasing the number of categories that a model is segmenting. So instead of just looking in a binary sense at clouds or not clouds, here we're trying to segment the presence of water, the presence of fields and grassland and trees and built up areas like buildings. And there's a very cool demo, which I won't go into, but you can click on the link in the slide on your copy. This is a project by Microsoft's AI for Earth, and they have this really cool live demo that you can click around in, and they will actually produce those predictions of land cover segmentation on satellite imagery. Okay, so moving on to instance segmentation. Now remember, we're not just interested in knowing where all the pixels are, or sorry, what pixels belong to what categories, but we actually need to know individual instances of every object. And so this is an example from SpaceNet 4, which is tasked with mapping buildings from satellite imagery. And in the evaluation of that is pointing out that a model that maps these three buildings as one polygon is performing worse than one that correctly delineates all three buildings as individual instances. And this becomes critically important when you're talking about something like looking at building damage, for example, where you're trying to assess not just how many instances of buildings there are in an image, but you also want to know or classify the amount of damage to that building. And so in this example, we're doing both instance segmentation as well as building damage classification. This is a challenge that was run by Defense Innovation Unit's XV2 in the last year or so. And again, it shows you kind of the sophistication that's possible when you take a bunch of tasks and put them together with different kinds of imagery and different kinds of labels. And then I wouldn't get away without also talking about this, SpaceNet 7, which is coming out imminently. I think the challenge may be starting today or soon. But in SpaceNet 7, we're using planet imagery, which is, again, RGB satellite imagery. But the difference here is we're looking at imagery over time. So there's a monthly mosaic over 2 years, often referred to as a stack of images or a data cube. And we're not just concerned with segmenting every single building instance on a single image, but we need to keep track of those instances over multiple images over time. And so you can see in some cases, clouds, which is a problem, as Joe and Nikki mentioned in the last session, will obstruct our view and remove those buildings from sight. But models that do well in this particular challenge have to keep track of those changes and also keep track of true changes in building construction over time. That at time 0 on the bottom left, for example, there was only a dozen or so buildings, and at time step 23 on the bottom right-hand side, there are many more actual buildings being constructed. And so we're keeping track of both the polygons of every single building, as well as the unique identifier for every single building over time. Cool. Okay, so that concludes our very brief, but hopefully useful tour through different tasks. And now I'm gonna break every rule of presenting to an intro audience and present the slide with very little labels and a lot of information on it. But we will get through it, and I will do my best to explain what neural networks are. So neural networks for computer vision, or CV here, are often called convolutional neural networks, or abbreviated CNNs and COVNETs. And they are loosely inspired by how neurons in our brain work, how they fire over time as represented through math in a computer. And convolutional neural networks in particular are inspired and loosely resemble how our visual cortex in our brains process visual stimuli, so process what we see. And so just to orient you to what we're looking at here, what's basically happening is that you're taking imagery at the bottom left here. It's a street sign, a traffic sign that's a circular sign that has a number 60 in it. And it's breaking down the patterns of an image into smaller elements or features, as they're called. And so this might be shadows, this might be contrast between dark parts and light parts, this might be hard edges or straight lines or horizontal lines. But it's breaking down these component elements of what we see or what an image possesses in terms of patterns, and then building it back up. It's taking small pieces like edges and shapes and building that up into its own mathematical representation of what a sign is and what the number 60 is. But it's not doing this just, out of nowhere. It's doing this because we're actually providing it the label training data in order to learn that these particular shapes oriented in this particular way, in these patterns with these shadows and these colors represent something meaningful to us as humans. And we do this by providing it labeled data. And so we're giving it an image, and truly it's millions of images of signs, let's say, and we're labeling them to say, this is a sign, or this is not a sign, and this is a sign that has a number 60 in it, or this is a sign that has a number 70 in it. And so on the right-hand side, you see that for this classification task, you actually have all the possible categories or classes. And so you have the sign or not a sign class, and then you have the actual numbers, 30, 50, 60, 70, 80, 90, 100. And that gives you, or I should say, as the machine learning developer, you're providing the range of possibilities for the model to learn from. And then by giving it those labels, so that the label that this is a sign that says 60 on it, you're asking it to make guesses and punishing its guesses if it's wrong and rewarding it if it's right. And then in a very iterative fashion, the model learns that signs that have these shapes in these ways, in its own mathematical representation of that information corresponds to these labels, that this is a sign that says 60 on it. Okay, so I'm sure there'll be more questions. I'm trying to leave time at the end for answering as many of those as I can. And also there'll be more links to lead you to better sources of information, but hopefully that lays the groundwork for the next couple of slides. Okay, so now we're going to look at how segmentation model, deep learning segmentation model actually learns in a sense as it trains on more data, more labeled data. And so to orient you to what you're seeing here, the labels are at the top. And so you have a drone image of overlooking a couple of buildings and a tree in the courtyard of a building, for example. And then I've overlaid the labels on it visually so you can see in red and green and blue, that these are the outlines and the kind of interiors of building footprints. And so we're actually, by producing these labels, we're asking the model to segment pixel by pixel 3 different things. We're asking it to segment the full footprint in the middle here of the building. We're also actually asking it to segment pixels that represent just the boundary of each building. And then on the far right, we're asking it to also segment the areas that are closely neighboring separate buildings from each other. And this is a technique that is pretty useful when we're talking about building footprint segmentation. I won't get too much into it, but it's usually gives us better performance than if we were just to give it a label of the footprint alone. And on the bottom is actually the output of the machine learning model after each epoch of training. And so what that means, to break that language down, is that an epoch is one full run through all the training data that is available that you're providing this model to learn from. So in this particular example, we have 800 labeled images of drone imagery with buildings and these footprints, boundaries, and contact labels associated with them. And so after the model learns by looking through 800 of these and making guesses as to what pixels represent buildings, footprints or not, on all 800, you can see once this animation kind of cycles back to the beginning, that it gets better over time and by time I mean with more training examples at figuring out which pixels are actually representing buildings in the yellow versus not, which represent background in the dark purple. And so what's happening in each frame of this animation is that it's learning on one more epoch every frame. And so after the first 800, it's starting to get better and delineate, and kind of like classify the pixels of a building. But after 2 epochs, after 3 epochs, and all the way ultimately up until 10 epochs of training, it starts to get pretty good. Not great, but pretty good at saying these are building footprints, boundaries, and the contact between neighboring buildings. The other thing I'll point out here, which is important from a label quality perspective, is that we actually have an error in the label. In the top left, you can see that the building is below a tree. And so the tree is actually covering the corner of the main building in the center. And yet we still have a label that directly cuts through the tree and says that essentially these pixels that are actually tree pixels are building pixels. And that's actually reflected. You can see in the bottom that in the prediction, that area where that tree is not being mapped as a building, or the model is in a way struggling to classify that correctly as a building or not, even though the label says that should be a building. Because it's looked at 800 times 10, 8,000 examples of buildings and not buildings. And most of the time when it's a tree pixel, it's not a building. And so this is a case where a mislabeled pixel, or really many mislabeled pixels can adversely affect the performance. On the other hand, it's pretty annoying to have to label every, area of a building that's covered by a tree or not covered by a tree. And so it's traded off with, the amount of effort that you have to undergo as a human labeler of this data. How important is it to you that the model is actually segmenting around trees correctly or not? If it's not that important, then we can get away with this. If it is, then you might want to devote more effort to correctly delineating around those trees. Okay, so with that, we're gonna go through a few quick examples of what label quality looks like when it comes to building segmentation. And so this is the same task that we kind of looked through a few times here, where the green outline, the yellow outline represents the full extent of a building. The imagery here is high resolution drone imagery. This is somewhere around like 5 centimeters to 10 centimeters, depending on image. But you can see that in this case, the labelers have done an excellent job of drawing the outline around every single building. Even when they're very small buildings, even when they're buildings very close to each other, it's not just one big blob of a building, but you can very clearly see every building, to the best of their ability, is delineated, is separated from each other. And so that consistency and exhaustive labeling is a great sign of a high quality label data set. In this case, the quality is okay. It means that you can see most of the buildings are labeled, which means that most of the pixels are correctly assigned to either being a building or not a building. But in some cases, the geometries are offset. This red roof building here, for example, the shape is off by a bit. And so you could say that 80% of this is correct, but then the area where it's over the sidewalk and the area where it's missing the roof will lead to errors in training down the road. And so it still works very well, and that's the power of deep learning, is that with enough data, even if it's not perfect, there are enough examples to correct for some of these things. But at some point, if your data looks like this, you might want to think about investing more effort to improve the quality of the label. And then looking at really not good data, really data that would be hard to use as is when it comes to training these segmentation models. Some examples of why this is the case: a lot of buildings are missed, a lot of shapes are offset or just over nothing, over the road. And what happens is, again, remember, we're telling the machine learning model or the deep learning model what our understanding of the world is, right? So if we're telling the model buildings look like roads in this case, that a couple of buildings here look like the street, looks like concrete, or looks like the top of a car. With enough of those examples, it's going to start thinking the tops of cars are buildings. And that is an error. So this would be what a poor quality labeling job has done. Okay, so in the last couple of minutes, to make sure we have time for questions, I wanted to go through a challenge that we put together in a data set associated with the challenge through DFDRR. This is a partnership with Xavier and Driven Data in producing the data set and running the competition for it. But essentially, we put together this enormous new open data set for machine learning purposes of building footprints across over a dozen African cities and urban areas. All of these labels were collected by local participatory mapping groups, often through OpenStreetMaps. These are through programs like Open Cities Africa, Dar Rahmani Huria in Dar es Salaam, Zanzibar Mapping Initiative in Zanzibar. And I guess to commend their efforts, to say that these are all very local efforts to create the best possible manually labeled building footprint data out there in an area of the world that suffers from a lack of such data. Most of our training data about buildings exists in Europe and Americas and Asia, and to see more data put out there labeled by local communities that represent diverse African cities and urban environments will advance our understanding and our ability to apply deep learning models to those locations. The other thing that advances it is that we made sure to make all of the data as cloud native as possible. And so all the imagery is formatted as cloud optimized geotiffs, which I'm sure many people talk about this today. The labels are in GeoJSON formats, which is a standard well known. And then all of this information is organized within a spatial temporal asset catalog, which we'll look at next. We had accompanying competition with $15,000 in prizes that went to the best segmentation models, as well as the best entries exploring responsible AI principles and principles of ethics and responsible development of machine learning tools for these kinds of settings. You can look at those results at this link, and I really encourage you to do so. There's a lot of background information about the challenge, about the data set, about the purpose, as well as all the winners' solutions, which are open sourced and available for anyone to use for any purpose. And it's just a wonderful opportunity to explore. And so to go a little bit more into the data set itself, it's organized again as a stack to enable us to provide metadata in a consistent way, to make it really easy to query and to browse either manually through a web browser or also programmatically through code. And so I'll try to go to this link here and show you in a live way what this stack browser looks like. And so this is the kind of high level listing of the various collections within the training data set. We've just organized it by name into two categories. There's a tier 1 category, which is really high quality training data, and then tier 2, where the labels are not as high quality, but it might still be useful to ML developers. And then the 3-letter abbreviation for the particular location. So ACC represents Accra, Ghana. And so if we click into that, you can see through the stack browser, again, all of this metadata being visualized in a really powerful way, who the providers of this data are, what the version in the license for this data is, and for the stack catalog is. You can see where in the world it is. And so you can see that there's a bounding box around Accra, and there are 4 assets within it. And so in the first asset, if we go in, you can see that the imagery actually loads almost immediately. And even though this image itself, maybe in full resolution, is a couple of gigs in size, because it's formatted as a cloud optimized GeoTIFF, it will load as quickly as that particular resolution requires. And so as you zoom in more, it'll just load the high resolution image in that particular area and not the rest at the same time. And so if you're, for example, in a very bandwidth limited area or don't feel like downloading 80 gigs worth of data just to look at one image, this is an incredibly powerful way to quickly browse to just the area of the data you need. What else is really cool about this is that we're using the label extension, which is a kind of an add-on to the STAC core spec that describes the kind of labels within this data set for training, for ML training purposes. So we're seeing that this is a vector style or vector type label, which means that they're shapes. The labels represent buildings. There are 7,308 buildings in this particular asset. This is the license. This is when this image and label was created, etc. And if you go to this drop-down menu and open this, you can actually visualize those GeoJSON labels on the imagery in a very quick fashion. And so now you can actually see every single building footprint label visualized on top of the cloud optimized GeoTIFF. And then the links to each asset are also here, but you can go ahead and just preview the entire thing like this. And if you wanted to, you could also click on each one of the shapes and it'll give you all the properties of that particular geometry within it. And so this is, yeah, I think this is the first of this kind of data I've seen visualized and in a stack format like this, that's machine learning data. I encourage you to go to the link on your own and explore it and click around and see what you like about it, what you don't like about it, but more importantly, apply some of the things that we talked about today to understand what makes for good label data and not good label data and why. You can also download the full data set at this link, which is again at the competition website. It's about 80 gigs. So if you happen to have that much space lying around and bandwidth, then feel free to do that. Or you can just browse it online here, which will require much less data usage on your part. There are just a few links here I won't talk about, but if you want to learn more about deep learning, there are really wonderful online courses that are mostly free and they cater to different levels of technical proficiency, from having none, for example, to having to have like a year or so of Python programming background. There's also courses like Stanford's course on computer vision specifically, where you can just check out the course notes and the lecture slides. But what's really wonderful both about deep learning and geospatial data is that most of these resources and tools are open and free and online, and it makes it for a very accessible realm to learn more and get really good at. And so here are some tools that focus on both the geospatial side as well as the deep learning side. And that leaves me with just about 7 minutes. So I will try to answer a lot of questions, as many as possible. But if you have more and couldn't get to it, feel free to reach me at either of these things. And I will try to get back to you, maybe not as quickly as I can. There's a lot going on, but I will try to get back to you as soon as I can. All right, so let me turn off screen share. And let me know if you have any questions. Okay, any recommendations for using models trained on the OpenCities dataset to improve OSM? Yeah, for sure. So there's a lot of ideas that have come out of that process. So just for some background, most of the data set was from OSM data to begin with. So all of that data that was used for training purposes was originally pulled off of OpenStreetMaps. They were produced through these various local mapping programs, et cetera. And so there's already a gradient of quality between different cities and different teams. And so what we found through the challenge is that the top 3 and probably the top 10 leaderboard contestants on the segmentation side have used just the tier 1 training data to do most of the training, and then they use pseudo labeling on the tier 2 imagery So they didn't make use of the labels in the tier 2 quality or the lower quality data, but they made use of the imagery for it by applying predictions from the model trained on the tier 1 data to the tier 2 image to increase the amount of overall training data they have, even if the overall amount is not, fully hand labeled training data. It still provided a significant boost to mapping performance. And so when it comes to OpenStreetMaps, an interesting idea I have there is that, maybe pseudo labeling could be a very powerful way to assess the quality of labeling in a particular area. You can use models to predict on the image and compare it to the hand labeled geometries for area and see essentially what the overlap between that is. If there's really good overlap, then there's probably no need to do any corrective action. If there's very little overlap, then that's a flag that those polygons that were on OSM probably need to be corrected. Taking that to the next level is, well, can you actually use the polygons or use the predictions from the machine learning model to generate those polygons? I think there's a lot of nuance to that, and it's much more of a collaboration between human mappers and AI assistants to make sure that we're not just willy-nilly throwing a bunch of garbage polygons into OpenStreetMap. But there's a lot of effort that the hot team, the humanitarian OpenStreetMaps team is working on to enable this kind of ML human collaboration. Yeah, there we go. That's a great link. So ML Enabler is the right one. If you look in chat, that's exactly what we're talking about. Thank you. All right, well, let me just drop the link to the slides in the chat once more. And so if you have any questions, you can refer to it. Oh, the one thing I forgot to mention, actually, let me just share my screen real fast, is that I had a lot more slides. And so my appendix is probably longer than my presentation. And so if you wanted to, I'll just flip through this real fast, but there's a lot more details about the challenge, about a particular machine learning workflow for mapping building footprints on drone imagery that I go through. And so if you wanted to really dig deep into this, but didn't want to like search around the internet forever, this is a good way to get started. And we go through what it means to actually prepare and pre-process the data, how to split it into training, validation test sets, what it means to convert polygons to pixels for training purposes, what it looks like to evaluate a machine learning model in training, look at predictions, how to evaluate it after training using various and common metrics like precision and recall and F1 scores, et cetera. And then of course, there's a lot going around responsible machine learning throughout the entire machine learning development process that I didn't have a chance to talk about, but it's incredibly important. I'll also say on this note is that while the really maybe provoking and eye-catching part of all this is developing the machine learning model, I would say the vast majority of the work is what comes before and what comes after, and how well you label the data, how thoughtfully you are about what data to label in the first place. Because ultimately, the machine learning model, the deep learning model, can only do as good as the information you give it. And if the information you provide is a biased or incorrect representation of the world, or in a way that reinforces, inequity and power imbalances, then that will be represented by the model, because there's no other way for it to learn. It's just learning from whatever you give it. And so there's a lot of power and a lot of responsibility in making sure the data that you create and label and feed into training data models, as training data into machine learning models are correct and are fair and just. And then on the other side, that the outputs of these models are used in a fair and just way, that they will go wrong. They will make mistakes, and those mistakes will have adverse negative consequences on people, especially who are most vulnerable and unable to do anything about it. And so there's a lot of care and caution required in making sure that you're not just, again, spewing garbage into the world, that what you produce through this process is really serving the goals that you believe in and the goals towards a better world. So, all right, I'm off my soapbox. That is all of my slides. And again, you can find this all at this bit.ly link, which I will drop in the chat. So thanks, that is all of my time.
Thank you, Dave.